Okay, we're going to continue on here, organicing. We got into alkenes and alkynes last time. Again, a couple of more organic groups, which again are pretty much, as we've been talking about, really based off of the alkanes. The functional group here for alkenes is the carbon-carbon double bond. And that's our functional group there. And for our alkynes, it is a carbon-carbon triple bond. And that's sort of how we change the name from our alkanes to each of these is kind of the ending. So if you have a double bond there, ENE at the end, got a triple bond, a little YNE. A little bit different though than we do with alkanes, as we talked about last time, is in terms of priority. When we're numbering the largest chain, we do want to give the double bond or the triple bond the priority in terms of numbering. So it should have this smaller number as opposed to the groups, which is what we typically look at when we're doing alkanes. We also, a little bit different as well, around 4 carbons or more, you do have to give sort of the location of where that double bond or triple bond is located. And that kind of goes right in front of the base name of it, with a number and a dash in front of it. Once you lock in your naming or numbering there based on the double bond or triple bond, then any other groups that are attached are numbered accordingly, the same way as you did your double bond or triple bond. We also talked about cis and trans isomers. And remember, cis means basically the same side of the double bond. So you got 2 groups on the same side. And again, it doesn't matter if they're up or down, but they're on the same side. And trans means opposite sides really of the double bonds. So you got sort of opposite groups happening here, or opposite sides of that double bond. Remember, as we talked about, in order for a cis or trans to even be possible, you do have to kind of look at the double bonded carbons. And again, you need to assess each carbon that they have a different group attached to them. And you also need to assess, I have to use D, you need to assess that they have a similar group between them as well. So again, if you come across a carbon-carbon double bond where one of the carbons has basically the same group attached, then it is not possible for cis or trans. So sort of eliminates the possibility of that. Also a reminder that if you are naming something in cis and trans sort of deal, like this maybe. Now, remember, if you're going to name something like this, you still want to look for the longest carbon chain, even though it may be drawn in the cis or trans conformation. So as a couple of those examples like we did last time, remember, longest carbon chain is still all of those in this case. Again, you don't want to get sort of just caught on the carbon-carbon double bond and only count 2 all the time. Again, you're still looking for the longest continuous carbon chain. We finished up here talking about really alkenes and reactions that they undergo. They can undergo what is referred to as a symmetrical addition reaction. Addition reactions basically means that we just add 2 things into the molecule. And the adding always happens, as we talked about, usually at the functional groups, pretty much where all the action happens. So in this case, for our double bond, that's where it's going to happen. So always in this situation, if you got a double bond and you're adding something to it, we have to make room for it. And that's essentially what's going to happen. And remember, as we talked about, really nothing else changes other than you really should just make the double bond into a single bond. And that's essentially going to open up some real estate for those, in this case, hydrogens that are going to come in. And all you would do in this case is the thing coming in will always add to different carbons. So they never add to the same carbon. So they always add to different carbons in the double bond. And again, we could put an H there and an H there. Since this is basically H2, this is what is sometimes referred to as a hydrogenation reaction. And a hydrogenation reaction will take an alkene back to an alkane by getting rid of that double bond. Remember, when we put the double bond on, we lost 2 hydrogens. So basically the opposite move here. We're going to put the hydrogens back on and get us back to an alkane. Now you could do that with hydrogen like I did there. You could also do it with some halogens as well, like Br2Cl2. Again, it works the same way. You're just going to kind of make the double bond into a single bond, and one goes to one carbon and one goes to the other. Again, they're sometimes referred to as symmetrical additions because you're basically adding the same element to each carbon. So it doesn't really matter technically where you put it. Now there's unsymmetrical additions, which works basically the same way. And the difference, though, is in an unsymmetrical addition, you're usually adding hydrogen and something else. So, for example, when we do water, that's basically going to be adding hydrogen and OH. That's sort of how water would be added. And when you do have this unsymmetrical addition and you are adding hydrogen, there is a rule to follow that the hydrogen always ends at the carbon with the most hydrogens to start with. So what we're talking about is the carbons in the double bond and how many hydrogens they have. And if there is a difference in the number of hydrogens on those carbons in the double bond, then the hydrogen should go to the one with the most. In this example here, when we look at the double bond, there really is no difference, right? They both have 2 hydrogens, so it doesn't make a difference in this particular case. So you can really put the hydrogen wherever you want. But same idea, hydrogen is going to go to one, the OH again going to go to the other carbon. Nobody again adds to the same. We're going to do the exact same thing before we could actually add those guys in. We do have to make room for them. So we're going to turn basically the double bond into a single bond. And hopefully you can see, as I mentioned last time, nothing else changes. Yeah. So again, don't get creative with it. Don't get cute with it and draw weird things. Just pretty much draw what you started with. Just get rid of the double bond and make it a single bond. And at this point, we now have made room for our H to come in and also our OH to come in here. And this goes from an alkene to an alcohol here, which is that is the functional group there, an alcohol. You could also do this unsymmetrical addition with things like HBr, HCl, and so forth. And again, if there is a difference in the number of hydrogens on those carbons, that's what's known as Markovnikov's rule. You want to send that hydrogen to the one with the most. So I think we did one that kind of looked like this last time, I think. Try to draw it right here the first time, maybe. There we go. We'll go that way. And we'll do something like this. Squeeze the H in there. So if we did something like this and we added again something like, hey, let's just do HBr. And in this case, we're going to add H, we're going to add Br. Once again, it's all going to occur right here at the double bond. And that is really the only thing you should change. So I would highly recommend you just copy what's there pretty much, and you'll have pretty much 99% of the structure you need to draw. Again, making double bond into a single bond. And now again, by doing so, we have made room for what's coming in. In this case, though, when we look at this carbon, again, it's got 2 hydrogens directly attached to it. When we look at this carbon, it has 1 hydrogen. So in this case, there is a difference in the number of hydrogens attached there. So we do want to follow that rule, which means to give us our major product, the hydrogen should end up on the carbon that had the most hydrogens to begin with, which would be that guy on the right. And then obviously our OH, not OH because we didn't add water, but our Br would be better there. Hey, that's what would happen if we added water, by the way. But let's actually add what I drew there. We'll throw our Br right there. Should go right about there. And again, that would give us our major product. If you drew it the opposite way, that is sometimes referred to as the minor product. But again, in most cases, you want to kind of draw the major product. Yeah. Yeah. So basically, it's just the idea of carbon needs 4 bonds. So basically, those carbons at the end will only have 1 bond coming into them in most cases, unless there's a double bond or triple bond. But if they're single bonded, Usually those end carbons will have basically CH3s. And also same thing in the middle. If everybody's single bonded, they basically will have two lines coming into it, so that most will be CH2s. Again, unless you get some double bonds or triple bonds happening. You don't typically I I did it on that way because that is really the connections between the carbon and the oxygen is how it's connected. I probably wouldn't mark it wrong or anything like that, but traditionally that's maybe so how you would want to draw the carbon connecting to the oxygen because that's really how it is. Just like if, for example, if I put it on the right hand side, I probably would draw like that with the O first and stuff like that. Yeah. Other questions? Yeah. It is. So you do get a mixture of both, and depending on sort of the reaction, and there's a lot more to it in terms of mechanisms and stuff like that. But sometimes you get like a 80-20 split. Sometimes you maybe get like a 90-10. So it depends on the thing and what it is. But you usually will get sort of a mixture of both. But one is usually more of a obviously the majority of what you would end up getting. Yeah. Other questions? All right. Well. Let's continue on there. By the way, we also talked about cyclo alkenes as well, right? And again, those are our guys that have our double bond in the ring structure. And again, if we do need to give some numbers on this, remember that, if we did have some groups there, our A group even, we do need to number through the double bond like we talked about. So we can't go away from it. So our two options in terms of number, we go 1, 2, and 3. That takes us through the double bond. Your other option would be to start here and go this way. You can't go the other way, which is a shortcut there. And again, the numbering has to go through that double bond. We could also do these type of addition reactions with somebody in a ring structure. Works the same way. You basically just get rid of the double bond and pop those two things in those appropriate spaces. Any questions on any of that there? All right, so as we were talking about there, a hydrogenation reaction is basically converting our double bonds into a single bond, or taking our triple bond into like a double bond as well. Usually, as I mentioned before, sometimes you'll see some catalyst there on the arrow, and for our purposes, it really doesn't have anything you don't have to worry too much about it, other than, again, a reminder, a catalyst is something that typically will speed up the reaction, so it helps it be a little bit more efficient and occur faster than it would normally. This also is used, like I said before, with oils and fats. And guys, when you think something that's, again, says partially hydrogenated, that is what's happening. They're turning some of those double bonds that were originally there, which actually makes it more like an oil liquid sort of base, into a more solid one when you get rid of some of those double bonds. And again, that's how you get something like our margarine and stuff like that. All right, so why don't you try this one? Write the equation for the hydrogenation of 1-butene. So it's good practice for everything. We'll start with the 1-butene and then draw what you get when you add hydrogen to it. Yeah. Okay, so let's take a look. So again, remember, whenever we're going to name or draw something, we want to work backwards. So clearly we see an ENE, so that should automatically tell you it's a double bond in there somewhere, right? And the butene part of it, which is really from butane, tells us we're really starting with 4 carbons. So just like normal, what we were doing before, even though it's this part of a reaction, we're just going to start with just the carbons. And I'm going to draw my 4 carbons. And in this case, 1-butene means that is where the double bond's located. So again, you do have the option of putting it at one end or the other. I'm going to put it here. Now, since I'm going to kind of draw like maybe a product here, I'm going to actually draw out the hydrogen so I can kind of see everything. You could do it condensed as well if you wanted to. So this guy on the left here has 2 hydrogens coming in, 2 bonds coming in, which means it does need 2 hydrogens. The guy next to it actually has 1 hydrogen. And the guy next to it has 2 lines, which would need 2 hydrogens. Again, the idea there is to get carbon to 4 bonds. So our guy here at the end would need 3. So it should look something like this to start with. We're going to do the hydrogenation. That is a fancy way of saying we're adding H2 basically, right? So we're going to lay up a couple of hydrogens here is what we're adding. And pretty much our double bonds, this is the reaction, it's the addition reaction. So now that we got kind of our reactants, we should then just roll into what we know happens in this case. And once again, it is simply just that part that changes, right? So we're going to copy everything we just drew there on the left, except we're going to make the adjustment that we need, which is our double bond into a single bond. So I'm going to go down because I'm going to run out of room, I'm sure. So I'm just going to copy basically exactly here, making a single bond where our double bond was. We're going to then do that. We're going to do this, a little bit of this, a little bit of that. And now, again, the purpose of doing that is to make room for the hydrogens coming in. And let me just draw it a different color. Again, always in this addition, nobody goes to the same carbon. So always 1 to 1 carbon, 1 to the other carbon. Again, this is one of those symmetrical ones, which means they're both the same. So we're going to put a hydrogen here, and we're going to put a hydrogen here. And again, we go from 1 butene now to all single bonded with 4 carbons, which is butane, right? So we go from, again, our alkene to our alkane. Let's think of the too many owls there to start with there. I was starting to remember the ending. Any questions on that one there? And obviously what I drew there is more of the expanded structural form. Yeah. The double bond on the other side would, well, actually the product will look the same, except you could just make one of these two red on the other side, but it basically is the same thing. It's just turned around, so it's perfectly fine. And if you started with this guy with a double bond on that end, that's perfectly fine as well. Yeah. So since you're drawing it, you could put, like we said, you could kind of call carbon number 1, whichever left or right. But again, once you kind of lock that in, you want to make sure everything else is the same. But in the end result here, you'll actually end up with the same picture in this case. Yeah. Other questions? Yeah. All right. So mentioned before, one of the this is what happens is we could do these partially hydrogenation of oils. And what that does actually is these are fatty acid chains and they have double bonds. And what happens when you have double bonds and you put a bunch of fatty acids together is they don't want to sit nice with each other. So they get all kinked up. And instead of that chain kind of sitting nice, they kind of go all over the place. The result of that is there's not a really strong attraction between them. And that intermolecular force makes them more oils and like kind of liquid type thing. What happens when you remove those double bonds is you get this nice, clean, all single bonded chain. And what happens with those oils now is that chain will now line up really nice with all the others. And they're going to have a lot more interaction with each other. And it's going to become more of a solid sort of structure that occurs in that case. So again, that's how what we do when we make some margarine, some partially hydrogenated, just add some H2s in there and convert some of those guys over. All right, couple other here to draw. Why don't you do these? Let's see what you end up. And actually, let's actually make this one. Let's do something different. We'll do HBr. Okay, so let's take a look. Once again, this is actually a condensed formula. So if it helps you, you can redraw it out with all the hydrogens if it makes it easier for you to see kind of what's going on. And again, if we kind of just redrew this out to start with, we got something like this. We're again adding hydrogen, which is H2. And remember, again, this should really be the only spot we're majorly concerned about to change. So you could almost just start drawing it, really. So we'll just do this, this, and this, and now again, we got to go single bonded there to make some room. Then we got a C, an H, and a CH3. At this point, right, we're going to add basically hydrogen in to each of those locations where we made room, and I'll just make a different color here. We're just going to kind of pop those two hydrogens in there, hopefully. Any questions on that one there? Okay, so here, even though it's a ring structure, still the same thing happening in this case. So remember, there is actually a hydrogen there to start with, and also a hydrogen there to start with. And there's really the same number of hydrogens on each of those carbons. We're going to do really the same thing. This is the only spot that's really of concern to us. And we're going to do that into a single bond, which would look like that, basically. At that point, we're going to add H and Br. This is unsymmetrical, but in this particular case, they both have the same number of hydrogens, so it really doesn't matter where you put either one. So I could put my bromine down here. If you want to, because it technically is line structure, you really don't technically need to put the H in there, but you can because it's assumed to be there. But if you want to, it's fine. And it'll look something like that. You could have also done it the other way because in this particular case, all you have to do is just turn the ring and then it'll be the other one that you drew basically because it'll turn around in this case. Any questions on that one there? Okay. And like I said, in this case, you could have put the BR there and the H there is perfectly fine in this particular case. All right. So obviously we also talked about the hydration reaction and works the same way. Again, going to make our alcohols. All right. I think we kind of did that one. All right. The next thing we're going to talk about is actually aromatic compounds. And aromatic compounds are really a group of organic compounds that contains a special type of ring structure. So this is benzene structure for benzene where those double bonds move around to the other side, basically. And oftentimes in your book and some books, because those double bond electrons are moving around, they will simply lay up benzene with a lovely circle in the middle to imply that, it's kind of moving around. So even if you see the one with the circle, you should understand that it still has those three double bonds, right? And it could be in either place. Also means that it has basically one hydrogen at each of those carbons, basically, right? So it's got one hydrogen sticking out basically at each of those carbons. That benzene ring should not be confused with some rings that look like it that we've seen earlier, like this guy that has no double bonds and terribly drawn there, which is cyclohexane, right? This one here that has only one double bond, right, which is cyclohexene. So again, in order for it to be benzene, it's got to have all three of those double bonds in there. Otherwise, it's really not benzene. These are not the greatest drawings right there. All right, so this again is a class of organic compounds. And like I said, probably for you guys, a lot of times they like to draw it. And I think in this book, more like that with the circle. But again, it's that 3-carbon sort of change. Now, there is certain benzene compounds that have historical names that people still use today. And here are 3 pack of that. If you have basically a benzene ring with a methyl group on it, that is what is historically known as toluene. So somebody says toluene, that's basically what it is. By the way, if you don't call it toluene, that is a methyl on a benzene, so that is methylbenzene, right? So you could call it methylbenzene if you like, but most people will still kind of call it toluene. It's like an historical history type name. A benzene ring that has a nitrogen containing group, an NH2, that is what is known as aniline, also a historical type of name for it. Sometimes people will call that, if they don't call that, aminobenzene is another name for it. And this one here, which is kind of like an alcohol, it's got an OH group on it, and that's what's known as phenol. So these are 3 names you probably should be familiar with because people still use them today, and it does sort of pop up along the way. And again, it's a benzene ring that has this group sort of attached on that there. Oh, things attached to benzene, or if we just have one thing attached to benzene, what we do is basically put benzene at the end and put the group there. So monosubstituted guy, which is chlorine here, is chlorobenzene. if we have multiple things attached to the benzene ring, we do need to give the numbering. The good news about benzene having 3 double bonds is you can't screw up the numbering, because no matter which way you go, you're going to go through a double bond. Yeah. So pretty much you're going to hit through a double bond. So you can almost just kind of go either way you want when you have a benzene ring, when you have those 3 sort of double bonds in there. So this is a chlorine at position 1 and 2, and that is 1,2 dichlorobenzene. Again, we do the same things we did, like, for example, with the methyl group. We had 2 of them here, so we used the prefix di. This is a chlorine at position 1, 2, and 3. This is 1,3-dichlorobenzene. And this is a chlorine at positions 1 and 4 on the benzene ring, which is known as 1,4-dichlorobenzene. I think there was a question a little bit ago about some names that sometimes we use with benzene, and this is the positioning that we use. So sometimes historically people don't use 1 and 2. This is what is referred to as the ortho positioning on the ring, the benzene ring, and it's sometimes just abbreviated with an O instead of the numbers, like O-dichlorobenzene. Yeah. The O means it's the ortho positioning, and it's at carbons 1 and 2 is what ortho basically means. It means those numbers. The 1,3 positioning is what is sometimes referred to as the meta positioning, and that also is sometimes abbreviated actually with an M. So you would use M instead of the numbers. And if you see the M, it means you got things hanging out at 1 and 3, basically, is where those things would be. And 1 and 4 is what is referred to as the para positioning. And again, sometimes people will just use a P to sort of abbreviate that. And if you see that, again, it means you have your groups at 1 and 4. So ortho is a 1,2 positioning on a benzene ring. 1,3 positioning on a benzene ring of groups is meta, and 1,4 positioning is para. So again, sometimes those are also very common things that you sometimes see when people are looking at benzene and the effort to shorthand things. All right. So those sometimes we'll use that a lot. Yeah. Question on that. And for each of those, you would do, for example, M dichlorobenzene or P dichlorobenzene. Yeah.
Still the same.
Yeah, they're a little bit different because of the positioning on the ring. So for example, if you just kind of rotated the whole molecule, they would still be in those positions, right? They wouldn't be like, it wouldn't move to like 1 and 2. So yeah. So then that's different than like when we're talking about, when we take like an alkane, if you just turn it around, if you just turn the alkane around, you know, that one that was over there now becomes the one over there. But these guys, because they're still locked into those positionings, they are different sort of compounds because of where those guys are locked into. Yeah. They're definitely related to each other. But sometimes depending on the positioning of those things, they will give them some different properties and stuff like that. Yeah. Yeah. And you would be correct as well. They would be technically isomers of each other because they would have the same formula as well. Yeah. 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 No problem. Other questions on that? No. All right. So if we had to name some of these here, again, kind of incorporating those kind of historical names. When we would look at this guy again, we basically have our benzene ring with that nitrogen containing group. And that again is where the aniline part of the name comes from. And because that's all kind of part of the major chain and that's an important group, that's going to be carbon number 1, where that group is located. And that's where we want to start numbering here. Go 1, 2, and then 3. And this would be 3-bromol aniline in this case. And again, we would number or name the group just like normal. Here, you may see it or not see it, but that right there is where we get the bit, which is again the benzene ring with that OH group. And again, number 1. And as I mentioned, because of the benzene ring, you can really go either way and you'll be okay in terms of the numbering. And as you can probably see, like they did here, if you go to the left or counterclockwise, that's going to give us our smaller numbers. Obviously, if you went clockwise, you would end up with some bigger numbers. We still want always, when you're naming, smallest numbers is kind of the preferred thing. And that's where we get our things. Again, alphabetical. So B before C. And I think there was also a question last time. Again, numbering is not important here. Again, we still want to go alphabetical. So even though the B has a larger number, it will still come first because it's alphabetical sort of rules on that. And lastly here, there's our toluene hiding in there, right about there. And again, we then have basically 3 groups attached. And in this case, we got 2,6-dibromo, 4-chloral. Again, all basically numbered off of this guy here. And really, in this case, if you went left or right, you'll end up probably with the same numbering. So, it's your choice, whichever way you want to go. Any questions on any of those there? All right, so let's take a look at these. What should be the proper name for each of these? Take a moment and okay, let's take a look. So clearly we got because that's hexane, so that's not good. Or cyclohexane. All right, so that's benzene. In this case, we only have really one thing attached, which means we really don't need the number here, right? So that's a chlorine group. So a little chlorobenzene seems like a winner there. Again, if there's really only one thing attached to the benzene ring, kind of like any other ring, it's always assumed to be carbon number 1, so you don't really need the number. So again, even if it was drawn like this, would still be chlorobenzene. It's just that molecule, as we kind of were just talking about, churn basically, and it'll still be at that same position. It won't move or anything like that. Any questions on that one there? All right, down here, I also see a benzene ring. So all of those are in play. I have a methyl group and a methyl group, so that's dimethyl. So we're good on all those so far. Well, you got to pick one of them to be one, right? So why not pick the top one? You could actually pick the other one if you like to call that one number 1 as well. The shortest distance to the second guy would be going clockwise, I think. So 2 and 3. So a 1,3-dimethyl benzene. Again, if you chose this as your number 1, you would go counterclockwise. And again, you would end up with the same numbering if you went that way. So that's all good. By the way, if you want to get all fancy with it, that's also toluene, and it's like 3 carbons over would be 3-methyl toluene if you want to get all fancy and old school with it. But this first name over here is probably good, I would think. Yeah. Any questions on that there? All right. That's a lot of decision tree there. Yeah. All right, that wraps up chapter 11. No. All right, I want to take a 5-minute break now. It seems like a good breaking part where I find the next lecture. Come on back. Okay, we're gonna get started back here. We're off to chapter 12 of organicness, and we're gonna get some more organic molecules here. We're gonna talk about alcohols, thiols, ethers, aldehydes, and ketones. Oh my, that's a lot of functional group happening there. So we're gonna talk about our alcohols, which have functional groups of OHs, some sulfurs, some more oxygens. So a lot of oxygen-based organic compounds here. So let's talk about each of these, and we'll get into each of them more specifically as we go through it. Alcohols. Let's talk first off about the functional groups of all these guys. And again, you should be familiar with the functional groups of what they are. Alcohol's functional group is an OH. So that is what makes something an alcohol. A thiol is kind of similar to an alcohol, except that it is sulfur based, and it has a functional group of SH. Ethers have a carbon, oxygen, carbon run of each other. So if you see that sort of little part there, that's going to be an ether. Aldehydes have a carbon, oxygen double bond and a hydrogen hanging out there at the end. And lastly, our ketones have a functional group of carbon, carbon, carbon. You essentially need at least a 3-carbon run. And in the middle of the 3-carbon run is a carbon oxygen double bond. So these are the functional groups of each of these guys. And again, we're going to go through each of them obviously individually here. But those are, again, as we've been talking about, pretty much what makes these guys, these different types of organic compounds. And as we'll talk about in a lot of reactions that we may talk about. This is, again, much like we saw with the double bonds. This is where all the action is going to happen, basically, at the functional groups is essentially where most of the stuff occurs. By the way, in organic chemistry, sometimes people don't kind of write C for carbon. And when they talk about, these things, sometimes you'll see like an R used. And the R basically just means you'll sometimes see like, ROH. And R is just I don't know how fancy of a way it is, basically, but it's basically just indicating that it's a carbon group basically attached to it. So that's a carbon group. And so sometimes in books and stuff like that, they'll use like R and like the functional group. And if you see that, it basically just represents a generic, some carbons attached and stuff like that. It probably made sense to somebody at one point, but that is what you'll sometimes see. But again, these are our functional groups for each of these different types of ones. Also, as we'll talk about, they all still go back to those 10 alkanes. So they all go back to really the alkane names, even all how we name all these guys. They all do fall back to those first 10. So alcohols, as I just mentioned a second ago, it's got to have an OH on it. And as you can see here, that's a 1 carbon alcohol. So 1 carbon is based off of methane. And we put OL at it, and now we get methanol, right? So it kind of works the same way. There's our phenol we just talked about, which is our benzene based. Again, our ether has to have that kind of carbon, oxygen, carbon sort of arrangement here. A reminder again, when it's written in condensed formula, although it may appear the hydrogens are connected there, the connection here is this connection between the carbon and the oxygen, and those hydrogens are actually attached to the carbon here. So remember, sometimes with condensed form, it may appear the hydrogens are being attached there in the middle, but they're not. They're always attached to the carbon as well. There's our thiol group again, as I just mentioned, which is our SH in this case as well. And in terms of line structures here, it does kind of work similar. If you have something like this, again, they will draw a line and put the OH there so you know it's not a methyl group, right? So you know this is an alcohol. Same thing, if you had an ether, they will actually just insert an oxygen in between. And again, that's your carbon, oxygen, carbon sort of run that you need for that ether to occur. And obviously, as you can see here, they'll put the SH in there for your thiol. So we're going to first talk about alcohols, and alcohols, again, with that OH functional group is what tells us it's an alcohol. We just finished basically talking about how we make an alcohol, and we can make an alcohol by simply taking an alkene, as we were just talking about, right? And we could add water to it, right? So we basically could add water to it and a hydration reaction, right? So we could do a hydration reaction to make an alcohol. And as we just talked about, we are going to single bond that guy in the middle. And one of these guys will get the OH. The other will get the H, right, from the alcohol, from the water, just like we just did. We again now created an alcohol that has 2 carbons based off of ethane. We created ethanol, right? The good alcohol there. And that is our OH group there. It only has really one location as to where you can put the OH group. In the case of ethanol, you could either put it on the right-hand side, like I did there, and that would be carbon number 1. If I drew it this way, the OH group would end up on which carbon? It's actually still carbon number 1, because the way that we number the chain is, in this case, much like double bonds and triple bonds, it is the OH that takes the priority. So we want to number the chain whichever way gives the OH group here, the functional group, the smallest number. And in this case, it would be the same, which means we actually don't need a number here. So we actually do not need a number with alcohols until you get to about 3 carbons. Because when you get to 3 carbons, I'll get rid of what I drew here. Maybe I'll get rid of what I drew there. Maybe I'll go away. There we go. So if we took this guy, slapped an OH there, and I take this guy here and put an OH there, each of these has how many carbons? Each of them has 3 carbons. So they're both based off of propane. Again, because they do have this alcohol group, they become propanol, OL, like the alcohol, yeah. Now we do need to number these guys to give the OH the smallest number. So looking at the top guy, we could go 1, 2, 3, or we could go 1, 2, 3. It doesn't really matter in this case. 2 is a winning number here. And this would be much like how we name our double bond or triple bond, 2-propanol. The 2 in this case is for the location of that OH group. It's on carbon number 2. So just like you kind of give the location where the double bond or triple bond is, you can give that. The reason we need to do that starting at 3 carbons in this case is the OH group on this guy is on which carbon? Carbon number 1 would give the smallest, right? So this is what we call 1-propanol, which is different than 2-propanol. And by the way, 2-propanol, right, is our isopropyl alcohol. It's our rubbing alcohol, basically, right? So multiple name, same thing. Welcome to organic, right? But these are 2 different ones as well. Again, because of the location where the OH group. So with alcohol starting around 3 carbons or more, just like you do with double bonds or triple bonds, you do need to give the priority in terms of the numbering to the OH group to give it the smallest, and you do need to give it in the name. And then obviously, much like you do with double bonds or triple bonds, whichever way you decide to number the OH, everybody else gets basically numbered the same way, right? So if I had something like this, I just try to make it up here and see how we do. All right, why don't you give it a go, see what you end up with in terms of a name on this one. Okay, so let's take a look. So we do want to basically follow the same thing we always follow, which is we want the longest carbon chain. In this case, what probably needs to be included in that? It needs to be the carbon that has the OH group, right? So just like when we did the double bonds or triple bonds, you got to at least have that double bond or triple bond in there. The longest carbon chain does need to have the OH group here, which is the functional group. So in this case, it's just straight across basically, right? That's got them all. That's 4 carbons, which again is based off of our alkane, which is butane. Because we have the OH group, it's now an alcohol. So it becomes butanol. We do need to number the chain. And again, we want to give the OH here the smallest number. We could go right to left here, and that gives it a 2. Obviously, if we went left to right, that is going to give it a 3, which is a larger number. So we would not want to do that. We probably want to go in this direction. That means that my OH group is at carbon number 2. So this now becomes 2-butanol, the 2 for the location where the OH group is at. And now I still have another group I put on there, right? Which is a chlorine, and that's a chloral group. Because once again, I did number in this direction for the OH group, I got to keep that numbering for this guy, and that puts it at carbon number 3. Again, you can't switch it up. You got to lock it in one way and keep it for everybody. And that would be like a 3-chloral 2-butanol. Yeah. Any questions on that one there? Yeah. That was a lot of numbers. So let me try that again. So you said pentanol, did you? So you have like the picture you're talking, right? So you're talking like you have the picture? You have the structure drawn to you? And you're trying to name a structure, or are you? Okay, that's what I'm saying. So, all right, that's okay. So, okay, I got pentanol. So tell me where I got everything now. I got what now? So 3 pentanol, a little OH there, and 2 on the left or 2 on the right? 2 on the left. Okay, so something attached here. Yeah, and 4 from the left, right? Okay, over here. Okay, gotcha. So in this case, yeah, we want to make something different. Let's make something different. That way it may matter. In the case if they were both the same, like the two CLs, you basically it would be the same. You get the same numbering because in this case where the OH is located is in the middle, right? So in terms of the OH, I'll put the other one back up and we'll look at both and just show you the kind of difference here. So obviously there's hydrogens there as well, so I'm not going to draw them all. But in terms of the OH, we would start with that like normal. And again, top one, bottom one, it doesn't matter which way you go, right? It's going to hit a 3 for that OH group, right? And the same thing down here, if you numbered this way, or you numbered this way, you're going to hit a 3 for the OH. So in this case, when it's like a tie, the next thing you want to go to is what is really next important. And in this case, what would be next important is actually the groups that are attached. So we'll do the guy we'll go do this guy here, right? Now it does make a difference, perhaps, for the groups, even though they both have kind of the same numbers, right? And one way the chlorine has a 2, right? And the other way the bromine has a 2 and 4 for the other one. Now, which way would I probably want to choose is based on how we would put our groups in the name. And we would put our groups in the name alphabetically. So we might as well, since it doesn't matter technically which way you go, you want to probably go in this direction because B is before C, and that would give that guy the smaller number. And down here, it really doesn't matter, right? Because they're both chlorines. So you got dichloral and it's 2,4 no matter which way you go. So this one, it doesn't really matter no matter which way you go. This one, it kind of does matter. And that's what you want to think about is, okay, you want to start with the functional groups, you get the smallest number. If it's like a tie, which happens a lot sometimes, the next thing you want to think about then is the groups attached. And if they happen to be the same groups and it doesn't matter which way you go, you get the same numbers, it doesn't matter. But if it does, like in the top example there, then you want to kind of default to groups alphabetically, giving that guy the smaller number. Other questions? Yep. All right. So as you can see in some of the examples we just did, we're going to go OL at the end. 3 or more, we got to start giving the number of the OH group, again, the smallest. And then again, everybody else is named the same way. Yeah. Yeah, so the alcohol is really the main organic thing. So kind of like when we had an alkane or an alkene or an alkyne, that is like the base of the name. So the alcohol in this case, if it's an alcohol, that should always be the base of your name. Okay. Yeah. Other questions? Okay. All right. Yeah, let's try some. Give it a name. Hopefully it's not the one I just made up a second ago. It might have been. I don't know. It's some organic thing. Give it a name. Start straight across and see this 1, 2, 3, 4, 5, 6. I think that's going to be a winner. You could also, by the way, get 6 if you want to go 1, 2, 3, 4, 5, and then go up, right? You could also get 6 as well. And again, it really doesn't matter which way you choose. They should probably come out the same. But again, if you have kind of that straighter long chain, sometimes it's easier to kind of just to look at that one. That means in addition to the alcohol, we also have a methyl group hanging out over here. So was that 6, right? So 6 with an alcohol, It's going to be based off of hexane, and this will be hexanol. Because it's more than 3 carbons, we also need to give the location of the OH group. And you can probably just visually see that going right to left is going to give the OH here, this smaller number. So that is a 1, 2, 3, 4, 5, and 6. That means that this now is 2-hexanol as the location of the OH group. Because we do have to lock in our numbering going in this direction, that means that our methyl group is actually at my really badly written 5, I think. So that is a 5-methyl 2-hexanol. Any questions on that one there? All right, my line structure here. Line structure. I mean, it's going to go straight across and see. So 1, 2, 3, 4, 5, 6, and 7. You again also, much like the one on top, if you wanted to, you could also go up there towards the end, and you could go 1, 2, 3, 4, 5, 6, and 7 that way if you wanted to. So again, they both at 7 looks like the winner. Just like we talked about previously, it is usually a really good idea to, check all your options just in case to make sure you didn't miss anything. A reminder, just like normal, you got to go in one direction till you hit a dead end. You can't go backwards. That's the only kind of rule there. So I got 7 in that case. And I do have an alcohol group there. So that's going to be heptanol, OL, right? Based off of heptane. Again, we need to give the location, and hopefully you could also see probably going left to right in this case. Should give that OH the priority in the smaller number. So we would want a number in this direction. Again, if we started in this direction, we would have a larger number for the OH, which is not what we want. That puts the OH there at carbon number 3. So this is now 3-heptanol. And we also still have one more group hanging out there we don't want to forget about, which is the lonely line there, right? Right about here. And that looks like it is at carbon number 6. And that should be a methyl group, right? If there's nothing at the end of that line. So this would be a 6-methyl 3-heptanol. Any questions on that one there? All right. Let's take a look at a couple more here. Why don't you also draw some here? What do we want to draw? I don't know. Let's see. I don't know what we want to draw. Let's see. Let's draw let's draw 4. Let's draw 4-bromol 3. Now we'll do let's do pentanol. See how that turns out. All right. Let's also draw let's go with 3-ethyl 2-methyl cyclohexanol. See how that one turns out. I don't know. Could be I'm just making this up, and I probably am. There's got to be an organic compound somewhere with that name, maybe. Methyl cyclohexanol. See, I'm trying to visualize in my head what it might look like. All right, give it a go. Let's see how surprised we'll be. Let's see. All right. All right, so draw the 2 on the right there, name the 2 on the left. If possible. No, it's good. It should be possible, hopefully. So again, we're looking longest carbon chain has the OH in it. That looks like a winner. Once again, you could also go that way and up. We'll get you the same. That is 5. So that's going to be a pentanol. All right, OL. We do need to give the location here, obviously, of our OH group. So going right to left, that's a 1, 2, 3, 4, 5. Again, that's going to give us really the OH with the smallest numbering. If you go the other way, the OH has like a 4 for the numbering. So that's going to now become a 2-pentanol for the location of the OH. Since we locked in the numbering that way, our last group there, which is a methyl group, will be at carbon number 4. And that'll be a 4-methyl 2-pentanol in this particular case. Any questions on that one there? Bottom one, longest carbon chain that has the OH group is this guy. That is a benzene ring, yeah, with an OH group on it. So that is our favorite guy known as a phenol, right? So that's what we were talking about there at the end of the last one. Now, because that OH is part of the main one, that OH will definitely be carbon number 1. And again, in the case of the benzene, you could go either way. In this case, going counterclockwise is going to give our bromine there the smaller number. So that's going to be a 3-bromol phenol. Yeah. Any questions on that one? Yes, ma'am. You you probably wouldn't because that's more of a historical name. Technically, you would have to then name the OH as like hydroxyl or something like that. So it has to use a different sort of name for the OH as well if you did that. Yeah. Other questions? All right, let's draw. Always drawing, we're going backwards. We just got a lot more stuff to draw, maybe, or maybe not. So OL at the end of that tells us it's definitely an alcohol, right? And the pentane part tells us it's 5 carbons. So that seems like a good place to start. Let's just start like normal with just our 5 carbons. 4 and 5, I could count maybe. OL is an alcohol, and that alcohol is on which carbon? It is number 3, right? So that's what that 3 means. Again, since you're drawing, you could go left to right, right to left. I'm going to go, don't really matter. I'm going to go left to right. I'll go that way. That's going to be my carbon number 3. That takes care of that name. And I'm going to call this one for me carbon number 1, which means in this direction here for me, that's going to be carbon number 4, which is our bromine. And now hydrogens, right? Just like normal. So we'll need 3 there. We'll need just 1 there. Also just 1 as it has 3 bonds. 2 and 3 in this case. Again, this would be one where if you had the picture, you might name it differently, right? So you might actually name it 2-bromo, right? Instead of 4, yeah. Yeah, you could do, yeah, if you did the line, that's perfectly fine. Again, you'll start the same way, 1, 2, 3, 4, and 5. And again, same idea, you just maybe put an OH there and a BR there, something like that. Other questions? Okay. And obviously, if you kind of did it the other way, it's basically the same molecule, just turn, basically, yeah. All right, so let's try this one, cyclohexanol. I had my doubts when I was writing it, maybe. That is what? That is a 6-member ring, right? Based off of cyclohexane. But because it's cyclohexanol, that 6-member ring should have an OH group, right? Doesn't matter where I put it. It doesn't, but wherever I put it, it is going to be carbon number 1. So I'm going to put mine right on top there just because, basically. Right? So because I put mine there, or wherever you put yours, that would be carbon number 1. And in this case, I could go left or right as well, just so you know, it don't really matter. I'm going to go clockwise in this case. For my number 2 would be right here, which would be a methyl group, right? And at number 3, which would be right next door, would be, what did I say there? An ethyl group, something like that. There you go. This should have no double bonds, right? Because if I put 3 double bonds, it now is phenol, right? And not cyclohexanol. I put 1 double bond, it is not cyclohexanol, right? So again, sometimes people get those kind of similar looking ring structures confused. So it does boil down to kind of double bonds. Are they there or not there? And, that's kind of making sure. Question on naming or drawing here. Yeah. You want me to draw the last one and condense? Yeah. So basically it'd be the same, except you just want to put the right hydrogen. So you can, we could do this, which would have 2. This guy would have 1. And also he would still have his OH coming up off the top. This guy here would have 1. And coming down would have 1, 2, 1 as well. And also he would have his methyl coming off. And this guy would have his CH2, CH3. And then we're going to come down this way to CH2 and come down this way. So try to squeeze it in there, CH2 as well. Yeah. So other questions? Yeah. Is your question?
Like we prioritize naming the OH.
I'm going to say we're not going to have that. So you don't have to worry about it. How's that? Yeah. So you'll either have basically cyclohexanol, you'll have benzene, which is phenol if it has the OH group, and that's pretty much all you'll have in that case. Yeah. Other questions? Yeah. You could, it'd be the same, yeah. So basically, if you just took that thing and just turned it, basically, it would be on that side. It's fine, yeah. Yep. And again, because we have no double bonds in there, it doesn't matter, where you kind of put it and stuff like that. On that, yeah. Other questions? Yes, sir. Yeah, the phenol is basically the benzene ring. Yeah, so that's the one with the 3 double bonds. Or a lot of times in your book, again, it's the one where they kind of just draw the circle in the middle. And again, that's that one basically, yeah. So that's what makes it basically a phenol. It has to have that benzene ring with those 3 double bonds. Other questions? All right. So again, ethanol, which is ethyl alcohol. Again, it could be made from the fermentation of glucose. It's the alcohol of alcohols, right? Here is glycerol, and glycerol is the main unit, as we'll see a little bit later on when we get into some of those biochemistry chapters. It actually has 3 OHs there happening. And it makes it really, really polar and works really well with water because there's multiple OH groups for it to interact with it. So alcohols work really well with water and really soluble in water because it does have that OH group that allows it to hydrogen bond with water. But solubility does decrease usually around 5 or so carbons. So if you have a lot more carbons attached with that OH group, solubility drops. But things like methanol, ethanol, those propanols and butanols, they are fairly soluble in water because they're not very big and they have that OH group, so they interact really well with water. All right, let's talk about some reactions that alcohols sort of undergo. So this is sort of an elimination reaction. An elimination reaction is sort of opposite of an addition reaction. Addition reaction, we throw stuff on. So this guy, we basically take stuff off. So when we dehydrate an alcohol, we get back how we made it. So if you remember, we made the alcohol by adding water to our double bond, right, through our hydration reaction. Right, so we went from an alkene to an alcohol. And in a elimination reaction or a dehydration reaction is we're going to take the water out. We're basically going to remove water. The way we put water on is hydrogen goes to one carbon, right? OH goes to the other. The way we take it off, same thing. We remove a hydrogen from one and then OH from the other. So where the OH is located, we remove a hydrogen from a carbon next door to it. So not the same carbon, it has to come from one next door. Since there is no next door neighbor this way that has a carbon, we got to go to this carbon to remove a hydrogen. And it really doesn't matter which one you take off, but you can take off any of those hydrogens on the left. When you do, that is how we get our water back. Yeah, so that is the water that's coming off. And just like when we put it on, we have to remove the double bond, right, to make room for it. When we take the water off, we got to put the double bond back on. And we put the double bond back on where we removed the water from. Now, if we have, nice to draw, maybe there's somewhere. Come here. There we go. So if we have an alcohol, say like this, maybe. Let's do actually this. So let's take this guy here and we want to go through a dehydration. By the way, that is sometimes just referred to as heat, a little triangle there. So when we heat up an alcohol, we're going to dehydrate it. In this particular case, definitely for sure, what's going to go is the OH, right? So the OH for sure has got to go. But in this particular case, do I have options for where I can take the hydrogen from? I actually do. I have two neighboring carbons, right? And I could take a hydrogen from either, but of course there's a rule in this case, because when we look at those neighboring hydrogens, do they have the same number of, there's neighboring carbons, do they have the same number of hydrogens directly attached to it? The one on the right has 3 hydrogens, right? Directly attached, right? The one on the left has just 2 hydrogens, again, that are directly attached to that carbon. These hydrogens are attached to this carbon, right? So they're not involved here, right? So when we put on the water, right, the hydrogen goes to the one with the most or the least number of hydrogens. The most, right? So oddly, when you take it off, you actually take the hydrogen from the least. So the one that has the least when you remove it, if there is a difference, right? So in this case, we actually would want to take this guy, and we would actually want to take this guy here, and that is going to give us our water, right? So that's basically going to give us our water. So how do I know what to draw next? I pretty much draw everything else that's there except for the water I just took off. Again, nothing much changes. So I'm just going to copy it, and you can see how quickly I could copy it because, well, this might be a situation where less thinking is better. Yes, you just copy what's there. Yes. So I have to do one thing though, because I took the water off. What I have to do, I need to put a double bond between the 2 carbons where I removed the water, which would be, I'll make it a different color. In this particular case, it would be right about there is where I removed it, I believe. And we would put our double bond in this case. This would give us what's known again as the major product. If you took the hydrogen off of here and double bonded between these carbons, that would give you technically what's referred to again as the minor product in this case. So again, that's kind of what you want to do. So when we put on the water, hydrogen goes to the most. If you want to take off the water, take the hydrogen from the least, if there is a difference. Now we could have had this, right? Which looked exactly like this. And in this case, we're going to take the OH. Doesn't matter. Carbon on the left has 3, carbon on the right has 3. In this case, you can take either. So you could pop it from any of those hydrogens from the right or the left, and it really doesn't matter in this case because they're both the same. They will give you basically the same product here. So let's just say I took it from the right here. I'm going to end up with this guy, right? Which will give me double bond here where I took it from. And we'll have this, right? Now, let's just say I took it from the guy on the left, right? If I took it from the guy on the left, I'm going to end up with this, where my double bond now will go between those 2 carbons, because that's where I removed the water from. This guy will be the same. Nothing else will change. And the reason it doesn't matter in this case is, if you were naming this guy, this is This is propene, right? 3 carbons, yeah, ENE. This guy is still propene, double bonds on which carbon? 1 on the top, and on the bottom it would be on 1, same thing. You get the same compound. Again, because there's no difference. There is a difference though when you do this guy, for example, as I actually made it bigger, I guess that's good. But if there is a difference if you did this guy, again, if we double bonded the guy to the right, which would give us our minor product, we would have a double bond like this. And we would have this, and this. And in this particular case here, double bonds located where on this guy? Carbon number, double bonds located where on this guy? Carbon number 2, no matter which way you go, 1, 2, 1, 2, you get different compounds, yeah? So again, this way where we have the least number of hydrogens gives us technically what's referred to as the major product. And again, if you took it the other one, you technically would get something different, a different sort of compound, related one, but again, I'll give you that one. Any questions on that there? Yeah. Yeah, so if your question is, does it matter if I took like this hydrogen, or that hydrogen? It doesn't matter. These are all equivalent hydrogens. They're all basically the same. So you could pull any one you want. Yeah. Other questions? All right, so that is dehydration. Let's talk about the other major reaction that these guys undergo, which is oxidation and reduction reactions. So let's talk a little about oxidation and reduction reactions here. Oxidation reduction reactions, when we're dealing with organic chemistry, is a little bit different than sort of what we did with inorganic chemistry. We kind of use our hydrogen and oxygen definitions here. And oxidation means that basically something has gained oxygen as you go from reactants to products, or it has lost hydrogen as you go from reactants to products. So these are really the definitions that we use in organic chemistry. Reduction is basically the opposite, is something that has lost oxygen as you go from reactants to products, and it has gained hydrogen, H2, as you go from reactants to products. So the gaining and losing of electrons that we kind of did in the kind of inorganic chemistry, we really don't use all those too much, those definitions here. We look more at, are we gaining oxygen, losing oxygen, gaining hydrogen, or losing hydrogen? So when we look at alcohols, we could classify alcohols the same way we could classify carbons. So for example, if I have this guy here, this alcohol is what is known as a primary alcohol. And it is a primary alcohol because the carbon that has the OH group is attached to how many carbons? Just 1, yeah? So kind of the same idea. If I had this alcohol, this carbon that has the OH group attached to it is attached to how many carbons? 1 and 2 makes it a secondary alcohol. And as you might guess, if I take this alcohol and attach it here, the carbon that has the OH group is attached to 1, 2, and 3 carbons directly. This is what is known as a tertiary alcohol. So primary, secondary, and tertiary alcohols, you look at the carbon that has the OH group, and we're looking at how many carbons are directly attached to it. Will tell you basically this if it's primary, secondary, or tertiary. This is really important in these type of reactions here, which are oxidation reduction reactions. Depending on the type of alcohol you have, it depends on what you will end up with in terms of what will happen. So let's talk about what you'll end up with by just doing it here. So we're going to start with a primary alcohol. And if we take a primary alcohol such as this one, I'm going to kind of draw everything out so you can kind of see where everything is kind of going. And if we do an oxidation of a primary alcohol, by the way, this primary alcohol's name is, how many carbons does it have? 2, and it has an OH group. This is ethanol, right? Primary alcohol. We're going to do a oxidation, which by the way is the symbol that you see there. So that means oxidation is occurring. So the definition of oxidation, one of the definitions is it is something that loses hydrogen, H2. So where is the functional group here? It is the OH. That's got to be involved. So this is what happens when a primary alcohol goes through an oxidation. We are going to lose H2. The hydrogens that come off are always basically these hydrogens. It is always the hydrogen that's connected to the oxygen. So that is one that goes off. Then the second hydrogen actually comes from the carbon that has the oxygen attached to it. Again, you could choose whichever hydrogen you want, but those are the two that are going to come off. Again, never from the same spot, always from the oxygen and always from the carbon that's attached to the oxygen. Those are where the two H's come off. That is going to give us our H2. Now, again, as you hopefully can kind of see a pattern in what we've been talking about, which is if I wanted to draw my picture, I should probably start with my original picture there, right? I should copy it exactly, except I probably should take off the hydrogens I just took off, right? So don't copy those hydrogens. So I'm going to copy it exactly. Once again, I am not changing a single thing in this case. I'm going to leave me a hydrogen there, and I also have an oxygen there, right? So if you remember perhaps what we just did maybe a second ago, or if you remember what happens when we put on hydrogen. So if we put on hydrogen to an alkene, what do we have to do here? Make it a single bond, right? So if we're going to make it a single bond, and we're starting with a single bond, and we want to actually put a double bond on, what do we have to do? We have to remove 2 hydrogens, right? That's exactly what we just did here, which means to finish out my structure, I should put in a double bond between where I removed those hydrogens. Yeah, we're going to double bond between the carbon and the oxygen. Basically the same idea as here, basically, right? It's kind of the same idea as doing this. So the oxidation of alcohols will always occur this way. Hydrogen from the oxygen goes off. Hydrogen from the carbon that's attached to the oxygen, double bond always between carbon and oxygen. Yeah, so that's always where you put it in there. Question on that one there. By the way, if we go backwards, that's the reduction reaction. We add the hydrogen back in, we take out the double bond to make room for it, and we put our hydrogens back in. So it works basically the same way going backwards. Yeah. So let's take a look at a secondary alcohol. So we take a look at a secondary alcohol, and I'll draw it as well. I will do this guy actually. Let's do this one. Oh, by the way, before we look at the secondary, let's go back to this one here and let's talk about what we actually just made. That's probably a good thing. We actually just made another organic group. This is known as an aldehyde. An aldehyde has our functional group we talked about a second ago right there. That is an aldehyde. If you had to take a guess, what would the aldehyde's name start with? Just like that, because there's still 2 carbons. And this is ethanol, ethanol, al at the end instead of ol. Yeah. So that is ethanol you just made there, which is an aldehyde. And again, it basically is the same thing as the alcohol. You just put al at the end of it, basically. Yeah. All right. So if you oxidize a primary alcohol, you will make an aldehyde. Now, what will happen here in our secondary alcohol? Let's take a lookie. We'll take this guy right here. This is 2-propanol, right? So you tell me, I'm going to oxidize this. Which hydrogen should go off for sure? The one that's attached here, right? And the second hydrogen should come from the carbon, right? That's attached to the oxygen. There's our two hydrogens going off. Now at this point, we just copy what's there without those hydrogens. Everything's exactly the same. Nobody moves. Last thing I need to do is to fix it by putting a double bond in the exact same locations we did in the previous one between the carbon and the oxygen. Looky there, I made me a new organic compound. That is a 3 carbons in a row with a double bonded oxygen. That is our friend that we talked about here, known as a ketone. Yeah, we just made a ketone right here. By the way, that has 3 carbons. This is known as propanone, O-N-E, because, you know, it's a ketone. It ends in O-N-E, so we'll call it propanone here in this particular case. So if you oxidize a secondary alcohol, you will end up with a ketone. And again, the hydrogens come off the same way. You also have the 2 hydrogens if you want to put it in there in the reaction as well that comes off. And again, those are the 2 to come off. By the way, just like the other one, that's the reduction reaction going in the backwards direction where you would remove the double bond and put the 2 hydrogens back on if you went that way. All right, to finish up, one last thing here, which is tertiary alcohol. It is quick. Now, if you take a tertiary alcohol, which is this guy, and I want to oxidize it, hydrogen that goes off comes from the OH, right? The next hydrogen comes off from the carbon, right? That's attached to the oxygen. Is there a hydrogen there? There's no hydrogen because it's a tertiary carbon, right? That's really problematic since I need 2 hydrogens to do this, right? You get a big no reaction. Told you it was quick. Yeah. So you cannot oxidize a tertiary alcohol because it's actually missing the second hydrogen that's necessary for the oxidation to occur on that carbon. So tertiary alcohol, no oxidation going to happen. Only primary alcohol gets you an aldehyde. Secondary alcohol gets you